you. Hello, everyone. I'm happy to be here today to talk about our work, the XOR cache, a catalyst for compression. Today's computing system allocate a significant amount of resources for caching. The last level cache can occupy a substantial portion of the die area. For example, as highlighted in purple, AMD Zen 3 dedicates around 40% of its die area to its 32 megabyte L3. While large caches offer increased capacity, this doesn't always translate into improved performance. Research indicates that a majority of cache hits come from a small subset of lines. What's more, large caches incur high latencies. Considering these, traditional large caches may not be cost-effective for future systems, given their disproportionate performance and cost implications. That said, computer architects have turned to efficiency optimizations. Cache compression is a promising line of research in this direction. By exporting redundancy within cache data, these techniques reduce footprint, effectively achieving the performance of a large cache using a smaller one. Cache compression method can be classified as intra and inter-cache line. Intra-line compressors take advantage of redundancy within individual cache lines, while inter-line compression exploits redundancy across multiple lines. Our work sits in between, exploiting the synergy between the two. At a high level, it performs interline XOR compression, leveraging redundancy from private caching and inclusion, which is common in today's cache hierarchy to do interline XOR compression. When combined with other techniques, it can further enhance the compression ratio. Now, let's dive into how our XOR cache works. We'll see this by comparing it against an uncompressed cache. Conventionally, cache lines are inserted as is, each taking its own physical slot. On a private cache miss on line B, the L1 on the right-hand side sends a request to the LLC, and the LLC services the miss by sending B to the L1. For XOR cache, when inserting A finds a similar line, B here, to perform a bitwise XOR with it. The XORed line, A XOR B, is stored in the LLC, allowing line A and B to co-locate in one physical slot. We highlight this interline compression ratio gain in yellow here. With every line pair effectively co-locate, the XOR cache achieves an interline compression ratio of 2. Also note that since A and B are very similar, the XORed line A XOR B ends up with a lot of zeros in it, which means we can further compress it to a smaller size using intraline compression schemes. We highlight this intraline compression ratio gain in orange here. And that's it for compression. Now let's see how decompression works when XOR cache services a miss on an XORed line. Suppose we have the same miss on line B from the private cache on the right. When receiving the request, the LLC forwards the XORed line A XOR B to the requester. In this case, the requester of B shares a copy of line A, so it reads out A to perform a bitwise XOR again to reconstruct B locally, and the miss is serviced. This is the high-level overview of XOR cache compression and decompression operations. Before we talk about its implementation, let's zoom in a bit to characterize XOR cache compression ratio, particularly how to find good candidate line to XOR with. We consider 3 cache compression baselines: base delta A mediate, base bitplane compression, and thesaurus. We profiled their compression ratio by analyzing LLC snapshots when running representative benchmarks. If we randomly select every 2 lines to be XORed, we will achieve some compression ratio boost. But can we do better? As we have discussed, we want a similar line pair A and B to be XOR together. Let's see in a concrete example. Here are two sample lines from running the body track benchmark. They are almost identical with just a few bits difference. When we XOR them, we end up with a more compressible pattern with many zeros, which means we can further compress this line A XOR B. In this specific example, A and B using intraline compression alone can be compressed to 16 byte each, making them 32 byte in total. Whereas with compressed XOR compression, they can be more aggressively compressed down to 8 bytes, showcasing XOR's ability to work as a catalyst for compression. With this insight, we consider an ideal XOR cache configuration by searching for the best XOR candidate for a line within its set, which we call ideal set. With this, our compression ratio improves from previous random configuration. If we further allow a line to search for its best candidate across the entire bank, which we call ideal bank, we'll achieve even higher compression ratio. This boosts baseline compression ratio by more than 2x. So, backed by these results, we show that XOR compression has great potential as a catalyst for boosting compressibility. Now, let's continue our discussion of XOR cache architecture. We have shown that XOR cache inserts an XOR line as opposed to individual lines in the LLC. This is handled by XOR's compression algorithm. On access, LLC forwards the XOR line to a private cache to reconstruct the missing line. This is handled by XOR cache decompression flow. Note that what we have shown is just one of the 3 cases of decompression. We'll talk about the others shortly. Finally, we will show that XORing is not always possible. Note that on XORing is fundamentally different from decompression in that decompression happens on LLC hits, and lines in LLC can stay as XORed with no problem, whereas on-XORing refers to cases where we need to on-XOR a pair to keep all of them recoverable at all time. We will illustrate these 3 things next when we discuss XOR cache coherence support. Here are the stable states of the MSI protocol for the LLC. Besides I, S, and M states, for clarity, we denote another state as 0, which is a special shared state with an empty shared list. An LLC line can only possibly XOR when it's in S or S0 states, highlighted in gray. Note that an M-state LLC line is potentially stale and has a more up-to-date copy in its private cache. This forbids reconstructing the original line, so we cannot XOR an M-state line. Here are the transitions between the stable states. Compression can happen on those insertion edges, transitioning within or into the XOR states. For example, on edge number 1, when servicing an LLC miss, the line transitions from I to S. This line can find another line to collocate. On transition number 2, when private cache writes back its dirty line, this line can also try to find another one to XOR with. On transition number 3, when LLC downgrades a line from M to S, the up-to-date line from private cache similarly writes back to LLC. It can also find another one to XOR with. Next, when XOR cache services a read request to a XORed line, it needs to decompress it. We highlight the related transitions in green. These are transitions 4 and 5. They are related to servicing getS requests from the XORed states. As we mentioned earlier, we have 3 cases of decompression. The first one is local recovery, and this is exactly what we have covered earlier. To recap, The private cache on the right-hand side detects a miss on B, sends its request to LLC, and LLC forwards the A XOR B line to it. B's requester itself has a shared copy of line A, so it can recover B using it. To sum up, line A is in S state, B can be in S or S0, and requester for B has a shared copy of A. In the second case, direct forwarding, the requester of B does not share the line A, but B has a sharer in the private cache, which is the one on the left. The LLC simply forwards the request to B's sharer. This is handled as any protocol that implements a cache-to-cache forwarding. In the last case, remote recovery, line B has no shared copy in the private cache, therefore in S0 state. And also B's requester does not share a copy of A locally. But there is another private cache, the one on the left, that has a shared copy of A. In this case, the LLC forwards its XOR line to it, it recovers B remotely, and then finally sends it back to B's requester. Note that the coherence protocol for the XOR cache guarantees that at least one in the XOR line pair has at least one sharer. Therefore, any request for XORed line will follow one of the three cases covered here. So far, we talked about compression, decompression. The last piece is on-XORing. This is needed in XOR cache to make sure every line is recoverable. We will need to on-XOR a line if any of them upgrades to M states. This corresponds to transition 6 and 7. We need to on-XOR if neither of them has shared copy in the private cache. This case corresponds to transition 8 on the last put as request. Lastly, we need to on-XOR when one or both of them are evicted. This is related to transition 9 and 10. Check out our paper for implementation of on-XORing and its implication on deadlock freedom. XOR cache adopts a decoupled tag data organization. Note that we also have a special structure called the map table shown on the right. At a very high level, the map table works as a hash table and is used to identify similar lines that should be XORed together. It is indexed using a map function with line data as inputs. Each entry stores a tag pointer pointing towards the standalone lines in LLC. XOR cache insertion flow is shown on the bottom, which is off the critical path. Using cache lines data, we compute the map function to index into map table. Recall that map table stores the tag pointers of the on-XORed lines. If map table misses, meaning there is no similar candidate for now, so we skip XOR compression and insert a tag into the map table. Otherwise, the map table hits, there exists a good candidate as their hash value match. We deallocate the map table entry, we read out the candidate's data and insert the XORed line. Check out our paper for map function design and XOR cache access flow. Here's a quick rundown of XOR cache evaluation. We use Gen5 Ruby model to run full system simulation of multi-threaded and multi-programmed workloads. We simulate a 4-core system with 3-level caches and size our compressed LLC according to the profiled compression ratios. XOR cache boosts compression ratio by 23% and 35% on multi-threaded and multi-programmed workloads. It reduces area by 1.93x and reducing power of LLC by 1.92x and power of hierarchy by 1.46x. It does incur a performance overhead of 2%, while it still reduces energy delay product by 26%. To sum up, XOR cache exploits redundancy due to private caching and inclusion. It performs interline compression and catalyzes intraline compression opportunities. It reduces LLC area by 1.93x, power by 1.92x, and EDP by 26%. And thank you. That's it for my talk.